In an earlier video, which I strongly recommend, I explained the hydrogen atomic emission spectrum. One way for high-energy hydrogen atoms to relax is by emitting energy in the form of photons. And the resulting emission spectrum is a series of lines of specific wavelengths or frequencies. Rydberg continued work from Johann Balmer and others to show that these frequencies conveniently can be calculated by inserting whole number integers into this equation, where RH is called the Rydberg constant. I recommend watching this earlier video before continuing. This is an important result in quantum history, in that scientists at the time were certainly curious about why these lines obeyed such a simple pattern of whole number integers in the Rydberg equation. The equation still does not explain why these lines exist the way they do. But it certainly had something to do with the atomic structure and the organization of electrons in the atom, which was still not fully understood. Enter Niels Bohr. For this video, part 1 of the Bohr model of the atom, I'll keep the discussion for general chemistry students, and I'll explain the classical quantum bridge in part 2 of this lecture. For general chemistry students, I'll keep it simple. Physicists in the early 1900s accepted the nuclear atom, which is that the atom is composed of a heavy, dense nucleus of protons and neutrons with smaller, lighter electrons filling the space outside the nucleus in some electron cloud. Bohr's model attempts to describe the hydrogen atom. Therefore, let's assume the image represents one proton in the nucleus and one electron outside the nucleus. And this image is not drawn to scale. The electron is far smaller than the nucleus. But what keeps the electron in place? Bohr's mentor, Ernest Rutherford, was the first to propose an orbital model, similar to the Earth orbiting around the Sun. Before moving on, it is important to note that this model is only for the one electron hydrogen atom. And the circular orbital model has major flaws that do not fit the quantum mechanical model of the atom, which was proposed by Schrödinger some 16 years after Bohr's proposal. Bohr, however, does derive the Rydberg constant and equation and helps explain the line spectrum of hydrogen. In part 2 of this lecture, I'll explain the successes and flaws of Bohr's model. Let's return to this discussion and appreciate the simplicity of Bohr's model and how it remarkably helps explain the hydrogen line spectrum. First, Bohr assumes that the electron is orbiting around the nucleus. This is one of the flaws of the model we'll ignore in this video, but Bohr also imposes quantization on the electron. He proposes that the electron can absorb energy and only be allowed to a specific higher energy orbital, but never in between orbitals. Similarly, the electron in a higher energy orbital can release energy by emitting a photon, and in the process, the electron will return to a lower energy orbital, and again, never in between orbitals. The limitation on the specific orbitals would help explain the specific lines appearing in the line spectrum. Indeed, Bohr did derive the Rydberg constant and equation for his model. Here, we see Bohr's energy levels of the electron are equal to negative Rydberg constant times 1 over n squared, where n is a whole number integer. The negative sign represents an electron is lower in energy compared to a free electron, as it is closer to the positive nucleus. And finally, as the electron transitions from a higher energy state to a lower energy state, then the change in the energy between energy levels is the amount of energy emitted by the electron. Hence, the specific frequency of photon. In this equation, the f and I represent the whole number integer for the final and initial energy levels, respectively. Let's do an example. Find the energy of light emitted and its wavelength for an electron that transitions from n equals 4 to n equals 2. In this problem, we want to look at an electron transition from n equals 4 to n equals 2, and these are the Bohr energy levels. So you have to imagine that there's an electron in a higher energy orbital or a higher energy state, and that electron will transition to a lower energy state. We'll call this n equals 2, and this electron is losing energy, and the energy is going to be lost in the form of a photon. And we know photon is equal to h nu. What we'll do in this problem is we'll find the difference in the energy levels. The difference in the energy levels is equal to the photon energy. So let's do this first. Here's our equation. Here's the Rydberg constant. Typically, this is reported in terms of joules when we're solving for these energy levels. And we have 1 over n final squared minus 1 over n initial squared. Of course, the final state is n equals 2, and the initial state is n equals 4. So let's go ahead and plug those in. As you can see, these are just numbers, and so we can get a value here. This is 1 over 4 minus 1 over 16. And when we solve for this, we'll get this value. We'll just multiply these terms and we'll get our change in the energy levels. Let's recall the purpose of the negative sign. The negative sign is the change, and that means that this electron has gone down in energy. It is now lower in energy than when it started. The other way we can look at this is that energy has been lost. Now, this is the change. That means that the photon energy is 4.086 10 raised to the minus 19 joules. And we know that the photon energy is equal to h nu, or we can replace nu with hc over lambda. So let's solve for the wavelength of this photon. We can rearrange this equation, and the wavelength is equal to hc over E. H is Planck's constant. C is the speed of light. And E is our photon energy. You can see from our units that our answer will have units of meters, which is a wavelength unit. So this makes sense so far. When we plug these values into our calculator, we'll get 4.86 10 raised to the minus 7 meters. If we convert this to nanometers, this will come out to be 486 nanometers. If you look on your electromagnetic spectrum, This is a visible photon. Thank you for watching. Stay for the next lecture, where I'll explain the flaws in the Bohr model and how Bohr used quantum mechanical ideas to help bridge the gap between classical mechanics and quantum mechanics.